Good morning or afternoon, everyone. I'm happy to be here. So my name is Pavel, and this session is about Windows internals for .NET developers. And so here's my Twitter handle, here's my email if you want to get in touch. So what are we going to talk about? Now, we all work in .NET, we love .NET, it's great. But as we discussed little briefly in the Birds of Feather yesterday, those who was in the performance room, you have to know the platform. And so you have to know things about the CLR, the garbage collector, and how to work correctly with the CLR. But this session is about another thing I think you should know, is how the platform works beyond the CLR. So what kind of operating system you're working on, and how can you leverage that knowledge to write better code, even when you're working with an abstraction such as .NET. When you're working with a high-level abstraction, you get ease of use, you get productivity, but there are no free lunches, and so you have to pay in some way. And so I think it's very important to understand how the operating system underneath your code is working. Because .NET can be viewed as just some abstraction over the Windows API in one sense. However, .NET cannot abstract everything. It's just not possible to do by any abstraction. So sometimes you want to go to the actual operating system. And so in this session, I'm going to give you some ideas what you can do by understanding how Windows works better and showing you some examples of things you can do. And of course, that should kind of give you an idea of how you can continue researching these things. So we'll start with a brief architecture overview of Windows. For you .NET developers and see where .NET kind of fits into the entire architecture of Windows. And I'm talking about Windows here, not talking about Linux or Mac. And even in .NET Core, you can still check whether you're on Windows and then do some things in a more efficient manner, perhaps. This is a very good thing to do. And then we'll look at some details about objects such as jobs, threads, general kernel objects, and briefly discuss the Windows runtime. So a little bit about myself. So I'm a developer, I'm a trainer. I wrote a few books. The last one is the Windows Internals 7th edition part 1. I actually even signed a few copies in this conference, I think 3. Jeffrey maybe signed 1,000, but I signed 3, so that's a good start. So I also wrote a book about WPF. It's a very nice book. It's like Harry Potter, but realistic. And so you should get that. I also wrote a book about writing applications in C++ for Windows 8. I think maybe 3 people bought that book, me, my mother, and maybe some other poor chap. Nobody writes Windows 8 applications. It's Windows 10 today, and definitely not in C++, usually in C#. So our books are in Amazon, so please buy them. It makes me money, so please go ahead, do that. Also have some courses on Pluralsight, most of them Windows internals, but there's another course on .NET interoperability fundamentals, if you care about these things. I have several open source tools that I write and host in my GitHub repo, so you can check them out as well. Mostly actually are in C#, some of them are in C++, because I kind of have to do that for writing drivers and some other system level stuff. I have 2 blogs. Actually, the first one just kind of went out of commission, so we can use both of them. Some people say it helps them sleep, so that's at least one thing good came out of that. So let's just start over. So I want to look at the Windows internals or the Windows architecture overview. So the first thing we see is their processes. These are things that are executing, such as Notepad, Visual Studio, Explorer, things that we know and love. And of course, our own processes written in .NET perhaps are also executing. Now, to do anything in Windows, anything meaningful, not just Windows, but actually any operating system, you have to somehow get to the kernel. Only the kernel can open files. Only the kernel can allocate memory. You have to get to the kernel somehow. So you have that red line separating user mode from kernel mode. And so you have user processes, so what can you do? In the native world, you will go and use one of those Windows APIs. We know there are many Windows APIs, thousands of them. And so you would call some documented Windows API. For example, if you're a Notepad and you want to open a file, you will call the create file function. and that createFile function will start to open a file, but really createFile can't really do anything. It can check parameters and stuff like that, but it's still in user mode, and so it needs to do some more things. So the next call that will be made by createFile is to a function which is in NTDLL. That is a very system-wide, very important DLL that has an API called the native API, which is completely undocumented. So there is some documentation, of course. Many people did some reverse engineering and stuff like that, but it is officially undocumented. And so createFile will call the NT-createFile function, which is in NTDLL. And NTDLL's main function is to make a transition into the kernel. I'll discuss that a little bit more a bit later. And so we get to the kernel with the parameters for NT-createFile. And this goes to a single function called the system service dispatcher. And this system service dispatcher just takes a number coming from the EAX register on the Intel and AMD platforms, and then uses that as an index to the system service that's actually being asked around. So if I ask for NT-createFile, that would be one number. I ask for NT-createUserProcess, that's going to be a different number. And so using this kind of table known as SSDT, the system service dispatch table, the specific system service or system call is going to be called. And it's going to initiate the operation to actually, for example, create the file, which really means that the I/O manager inside the executive, which is the higher level of the stuff called kernel, is going to build a request object and then send it to the appropriate driver, which may be, for example, the NTFS, a file system driver, or some other driver which is relevant for the request. And so this driver will eventually go to the actual hardware and contact the controller and say, hey, we want to create a file, let's see how that can be done. And so the kernel, the device drivers, they're all kind of combined powers to make things work. And so we have two layers in the kernel. One of them is called the executive. The executive is the larger part. It contains all the managers that are in Windows, such as the I/O manager, the memory manager, the plug-and-play manager, the power manager, the object manager, managers all around. The kernel underneath the executive contains the very fundamentals of what it means to be an operating system, things such as thread scheduling, interrupt dispatching, stuff like that, implementing kernel objects such as what the mutex does. This is done inside that smaller layer called the kernel. And device drivers are really the only legal option to get kernel new code into the kernel. And so anyone can write a device driver, at least in theory. And finally, we see there's a Win32k.sys there. This is the Windows subsystem kernel component, which is really the Windows manager. So if you're working with Windows Forms, WPF, then you create Windows, and there are child windows, all that stuff going around. So Win32k.sys is the manager of all that stuff. And so technically, the rest of the kernel doesn't care about UI much. That's why you can have Windows running on devices which don't have any user interface. That's completely fine. So it's kind of separated for historical reasons. I'm not going to go into that. There's the hardware abstraction layer, which is just exactly that. It abstracts access to the hardware, so I don't actually have to know the exact details of the hardware that relates to the CPU and, for example, interrupt controllers and stuff like that. I can use just kernel APIs, and the HAL knows how to do the right thing. Next, if we look at user mode, we have something called services. So services are normal processes that also interact with something called the service control manager, which runs the services.exe executable that you find in Windows. And so in .NET, we can write services as well. We just need to create a class derived from service base and override some methods on start, on stop, stuff like that, and you have a service. And so services get some management benefits, and they also can run under some special accounts, such as local system account, and of course, they can launch and automatically load even if no user is logged into the machine. So these are services, and they don't have any special powers beyond that. So they're not running in the kernel or anything like that. And then there's those that are called the system processes, which are processes which are kind of like they're doing their thing. Usually we don't really care about them too much, but it is important for them to be there, and some of them are critical in the sense that if they die for whatever reason, the system will crash with the famous blue screen of death with the error saying, critical process died. So things like the session manager and the service control manager, WinLogon that is responsible for showing the logon dialog with the help of some other process and stuff like that. These are system processes that are kind of always there. And then there is the CSRSS.exe, which is the Windows subsystem process. I'm not going to go into great detail of what a subsystem is, but Windows NT, which is, of course, the base of what we have in Windows today, started with 3 subsystems, POSIX, OS2, and Windows, and eventually every other subsystem just dropped along the way, and we only have a single subsystem called the Windows subsystem. And so every subsystem must have a manager process, which is CSRSS. If you look at your machines, you'll probably see 2 CSRSS processes, one of them running in session 0 and the other in session 1. If you're thinking about the Windows subsystem for Linux, say, hey, there's a new subsystem. That's not exactly the case, so it's implemented in a completely different way using another feature in Windows 10 called Pico processes and Pico providers, which we're not going to get into. And if you are running Windows 10 and you have activated virtualization-based security, then you actually are not running your own machine. You're not actually the king of your machine. There is a super king, if you will, called the hypervisor, the Hyper-V hypervisor. In fact, it is the one running the show, and it provides some benefits in terms of security. For example, there's a feature called Credential Guard, where your credentials are not stored in the LSAS process, but stored in another process called LSA ISO.exe, which runs in the secure mode, and so there's nothing you can do even from the kernel to access the memory of that process. And again, this is completely beyond the scope of our talk. So where is .NET in all this nice diagram? So this is .NET. We have the CLR and .NET Framework Class Libraries. They actually are sitting on top of the subsystem DLLs that expose the Windows APIs. And so .NET is completely in user mode. There's nothing kernel about it. Most of the stuff .NET does when it needs to do real things such as accessing files or allocating memory or creating threads and stuff like that, it just goes through the Windows API and then provides its own abstractions on top of that. In some cases, it may go straight to NTDLL, but these cases are pretty rare. Most of the time, it goes through the normal Windows API. So it's an abstraction, and naturally, it can't be a complete abstraction. But it is a nice one, and of course, we get ease of use and productivity for that. So that's great. That's kind of a general overview of the architecture of Windows, and fundamentally, it hasn't changed since the first Windows NT, fundamentally. And so .NET today is part of Windows. It's fully supported, so it's not going to go anywhere. I'm talking about the full .NET framework. So you should not be concerned about kind of dropping support for anything in .NET. It will never happen, probably. So it's only user mode. There was a nice project that you may be familiar with called Singularity, where Microsoft attempted to create an operating system written in C#, or a variant of C#, actually. So you can write actually device drivers in C#. That was a very interesting project. Unfortunately, they shut it down. However, you can still get the source code if you're interested. So it is possible to have .NET in the kernel, and I kind of wish it will happen maybe someday. And so this is not a complete wrap around the Windows API, which means we have opportunities to extend stuff and to optimize and do things that .NET just can't do because it doesn't provide the support. And .NET can never be as fast as Windows. Windows is always going to get new features, and even if .NET tries to catch up, it will always be playing catch up. And since .NET framework, the full framework, is not really going to be extended much because Microsoft needs to preserve compatibility as much as possible, then definitely Windows is kind of running loose and .NET kind of stays roughly the same. And even if you're working with .NET Core, you still, in some cases, want to leverage the actual operating system that you're running on and not just what .NET Core provides, even though it tries to be OS agnostic as much as possible. So let's discuss a little bit about Windows versions. In cases you actually want to use some special feature that only available, for example, in Windows 8 or Windows 10 or something like that, you need to check the operating system version in your code because you want to do things in the proper context. And so this seems like a very kind of straightforward thing to do, but not quite. So the first versions of Windows started with 3.1, and then it kind of got into 24, and Windows 2000 was internally Windows version 5.0. It all was just fine and good. Windows XP was 5.1, which really means that the changes within the kernel and the system weren't that great. So Microsoft decided not to bump the version number to a new major number. And Server 2003 was 5.2, everything was just fine. And then came Windows Vista. So Windows Vista had a lot of issues, but actually it wasn't the operating system itself. Vista actually was a very good operating system from the operating system kernel side. In fact, the Windows Vista Service Pack 1 kernel is exactly the same as the Windows 7 kernel, so it's not the operating system itself, but some changes have been made. So because there was a lot of time that passed between XP and Vista, Microsoft made a lot of changes within the kernel and the system, and so the major version number was bumped to 6.0. No big deal, right? However, many developers were writing code something like this. They kind of gotten used to Windows XP, and they were checking to make sure they're running on XP or higher. So they were checking the major version number, and minor version number should have been at least 1. But Vista broke that. And so many applications just say, hey, I need to run on XP or later. But I am running on XP or later. This is Vista. But the application just refused to run. So that was problematic. And Vista caused a lot of issues because of new stuff that was there. You probably are aware of user access control and things like that. And so Microsoft was really hurt by Vista. Vista is also a very powerful name. And it invokes expectations. You know what happens when you have expectations? You're going to be disappointed. That's almost for sure. Do you have expectation from this talk? You're going to be disappointed. Well, maybe not. We'll see. However, Microsoft learned from its mistakes, and then the next operating system was Windows 7. Notice the name. It's not Vista. It's just a number. I mean, it's not even a name. It lowers expectation. Where expectations are low, you cannot be disappointed because you weren't expecting anything. And so Microsoft really were scared of that version thing, and so they wouldn't bump the version number to 7.0. It was too dangerous. So they left that at 6.1, even though there were considerable changes within the kernel. And so that kind of solved that problem from the XP days. Those applications started running suddenly on Windows 7. Great thing. And so when Windows 8 came along, Microsoft was still pretty scared, so just 6.2, we're not going to bump the version further. And Windows 8.1, 6.3. And so then came Windows 10. It was embarrassing to set the version number to 6.4. And in fact, if you remember the beta versions of Windows 10, the version was 6.4. But in the final version, it was 10.0. Did Microsoft suddenly got some guts and say, hey, let's deal with all the stuff that's not going to work right now? Not really. So if you ask the operating system, what operating system version am I running, you're going to get back 6.2, like you're running on Windows 8. And so still the code continues to run. And so now comes the big question, so how do I know on which operating system I'm running? If I want to use some feature only existing in Windows 10, how do I check if it's Windows 10? It's going to say it's Windows 8, not good enough. And so we need to do something about it. So here's what we can do. So if I have, this is a very small application, an empty console application, and what I can do, I can ask .NET to give me the operating system version. So there's a version string in the environment, OS version property there. And if I run it, you can see it says, maybe you can see, maybe not, but generally it says that's Windows 8. And clearly I'm running Windows 10, I'm not running Windows 8. And so behind the covers, the .NET uses the getVersionEx function from the Windows API. And unfortunately, this function is now deprecated, so you should never use it. However, we're in .NET, so we're not using, it's not C++ here. So what we need to do is actually add a manifest file, application manifest file. And once we add that, we can see that at the bottom, there are some nice GUIDs which have been created to tell the operating system what kind of version the application is aware of. And so we can see these GUIDs, and because these GUIDs can't be guessed up front, so if I have an XP-based application, it couldn't have guessed these GUIDs, or Vista couldn't have guessed these GUIDs, then only new applications know about them. So if I, for example, uncomment the 8.1 version, and I run it, I get, this is 8.1, 6.3. And if I uncomment the last GUID, which is for Windows 10, then I'm going to get the real version of the operating system. So if you want to use features which are new, you have to specify these GUIDs in the manifest. So it's, in .NET it's pretty easy. You just add the app manifest file and make the changes so we get the correct information when asking about the operating system version. So as I said, it's not completely trivial, but not too difficult anyway. So that's out of the way. So when we're looking at the Windows APIs, there are various kinds of APIs. First, there's the classic Windows API, sometimes called Win32 even today, even though it has 64-bit versions, of course. This is the classic C API. There are thousands upon thousands of functions out there. And if you are trying to learn the Windows API, then good luck with that. I'd rather you don't do that unless you really have to. Only old guys like myself know how to navigate that API, and I still hate it. But in the Vista time frame, a lot of new APIs came out that were based on the component object model, or COM. How many people have heard of COM? How many people like COM? All right, that's more like it. So most people would rather COM die, but COM didn't die. In fact, it was resurrected in Windows 8 because the Windows runtime is all based on an enhanced version of COM. So COM is not going to go away. However, in .NET, in most cases, we don't actually need to know the gory details of COM, and the essence of COM is not really complex. It's just interface-based programming and location transparency. That's it. We don't know exactly where the server is, and we shouldn't care. And a lot of the Vista APIs are based on COM. Why? Because instead you have of having just those separate, deseparate functions which are C-style. You don't know which functions goes with other functions. You don't know if they are part of the same thing. At least now you have something which is object-based. You have an interface. You have methods. You say, hey, okay, this method and this method must be connected. They're part of the same interface. Kind of makes sense. And so many APIs today are actually COM-based. For example, if you work with DirectX, everything is COM-based that it was from day one. There's or day two actually. There's BIT, the Background Intelligent Transfer Service, which is a nice service that you can download and upload stuff in the background and let Windows or BIT service manage all that stuff for you. And there's Direct Show, Windows Imaging Component, and Media Foundation, which is the replacement for Direct Show, and many APIs use COM. And so that's the second type of APIs that we have today. The third one is the Windows runtime. So the Windows runtime is new, starting from Windows 8. In fact, it is completely native. However, it does have complete metadata, very similar to .NET. In fact, it uses the same metadata format because the metadata format in .NET is very rich. So it's being used by the Windows runtime. And essentially, this is just COM. And so from .NET's perspective, because we are always able to call COM components, using a wrapper called RCW, runtime callable wrappers, we can do that with WinRT as well. And the projection for WinRT is pretty nice. And we don't really, most of the time, need to understand the exact details of how these things work. And finally, there's the native undocumented API implemented by NTDLL, which is that last layer which is still in user mode, which actually makes the transition into the kernel. So here's an example. Let's say I'm in .NET now, and I'm using the file stream class, and I'm calling the read method. I do that sometimes. So because .NET really has no idea how to actually read something from a file, it has to go and call a Windows API. And so mscorelib or whatever library is there in .NET Core is going to call ReadFile. So ReadFile is a documented API to read something from a file. And that read file is going to call anti-read file from NTDLL. NTDLL is going to put the appropriate system service number into the EAX register and then issue an instruction to the processor, which is sysenter of 32-bit, syscore on 64 bits, which will transition the thread into the kernel. And this would get into the executive and call the anti-read file, which is exactly the same function as the anti-read file on the NTDLL side, by the way. It's the same parameters exactly, but NTDLL is just a trigger to move into the kernel, and the anti-read file on the kernel side actually does the real work. And so these kind of mirror functions, this is the way system calls work on Windows, in fact on other operating systems as well. And finally, this would call the appropriate driver to do the thing, which can be NTFS. If it's a real file, maybe it's a device, maybe another driver. And so this is kind of the call that happens every time you do an I/O operation. And so the same thread, starting its life in user mode, actually goes into the kernel, then back into user mode. And that's normal. So if you take a look at a tool such as Process Explorer, and you look at a .NET thread, you'll see that it has user time and kernel time. In fact, any user mode thread will have user time and kernel time, because it does go into the kernel from time to time to do system level operations. Only threads that only do some computations, for example, they don't need the kernel. But if you want to do anything useful, such as allocate memory, you have to get into the kernel. So that's normal. Thread just goes into the kernel and goes back. That's normal, happening all the time. So the first thing I want to kind of discuss as ideas for optimizations or ideas for extending the functionality .NET provides is something called a job. So a job is an object, a kernel object, which actually was introduced a long time ago in the Windows 2000 operating system. That means it's really, really old. But .NET doesn't provide any wrapper for jobs at the moment, and I don't expect that to happen anytime soon. And the idea of a job is that it can manage a set of processes, maybe one, maybe more, and provide some limits to these processes. And also provide some accounting information. So I can say, oh, let me know how much memory was used there, or how many processes are part of the job, because a process can create more processes that are part of the same job. And in fact, you can specify various types of limits, and if they are violated, you can get a notification through something that is called an I/O completion port, which is, again, is not actually wrapped by the Windows, by .NET in any direct way. And so this could be useful in many occasions, or in many situations. Let me show you or discuss some examples and show you one concrete example. So here are some of the limits you can specify for jobs. So you can specify the maximum amount or number of processes in a job. You can look at and specify the maximum CPU per job or per process CPU that you allow the job to consume, or process within the job to consume. You can specify an affinity. We'll discuss affinity a bit later, and priority class, which we'll discuss later as well. And you can also have a CPU rate control controlling your job. So let's say you have an application that does some background processing. Maybe you're doing some, maybe you're anti-malware application, maybe you're just doing some form of background processing, and you don't want to interfere too much with the main applications the user is working with. So how can you make sure you're not consuming too much CPU, for instance? So one way to do that is put your process or processes in a job and then apply a CPU rate control and say, hey, I don't want to consume more than 10% of CPU, because that would be too much to interference for the user working with some other application. And there's really no good, efficient way to do it otherwise. A lot of stuff is happening with jobs, and you can leverage that capability. And I'm going to show you that example in a moment. There's stuff about memory, how much memory you allow the processes to consume. Talking about physical memory, it's called working set in Windows parlance, and actual commit size, so how much you are allowed to consume, whether that's currently in RAM or maybe paged out. So again, there's no easy way to do that with other mechanisms. You can also limit the maximum bandwidth a job consumes. Maybe you have some application that downloads something from the web in the background. You don't want that to kind of take all the network bandwidth from the other process of the user, so you can limit that. And there's some other stuff related to user interface, such as clipboard access and the ability to exit windows, for instance, which I'm not going to show here. So let's see an example of CPU rate control in action. And so what I have here is an application that's running the Mandelbrot set. So the Mandelbrot set is something which I like very much. It's fun. And so I can build an application in .NET that shows the Mandelbrot set. And we can actually go ahead and zoom in into the Mandelbrot set and see the fractals that are created between the zones that belong to the Mandelbrot set, which are black, and the ones that don't. If you don't know what the Mandelbrot set is, please go ahead and read in Wikipedia or something. I'm not going to cover that. But in any case, we have some application. Maybe I want to limit the amount of CPU this application consumes. So currently, I can kind of look it up here in, let's say, Task Manager. And when I run it, I can see that it consumes roughly 10% of 10% roughly. And I can, of course, use some more precise tools to measure that. So let's say I want to limit it. So what I can do, I can actually use a job to do that. Now, because .NET doesn't provide any wrapper for a job, I have to create my own wrapper. So I have to do some interop stuff here in order to make that happen. And so let's look at how that's done. But first, perhaps let's see the final result, and then we'll look at the code. And so here's my command line here with the tool I wrote called CPU limit. And that's a very simple one that takes a list of process IDs, bundles up into all this process into a single job, and then applies the percentage I want to limit the CPU consumption. And so our process ID is 21420, as it says in Task Manager. Let's limit that to a 5% utilization. So I can set it. It says it was set successfully. And now if we try to run it again, what we'll see is that first it takes a little bit longer, of course. And the CPU consumption, it's not very easy to see, but it's kind of moving around 5%. So it's a bit higher, a bit lower, because on average, it's going to be 5%, and Task Manager is only updating once every second, and it's not too precise, but it is what's happening behind the covers. And so I've managed to limit my CPU consumption very easily by using a job. So let's see what that actually takes in terms of code. So what I wanted to do is create a job class, a new class that represents a job. And to do that, I'm going to use the job kernel object behind the cover. So I need to manage a handle, which is done in .NET using int ptr, which is the general way of saying here's an integer which is 4 or 8 bytes long, depending on the bitness of the process, that represents something that the CLR knows nothing about. Now, there are actually better ways to manage handles, which I'll show you later, but this is kind of the basic stuff. So I'm going to implement iDisposable. I'm going to have a finalizer, so I can close the handle whenever this object is disposed or being deleted or destroyed by the garbage collector. And so I have a create function, and I have a bunch of native methods here that are in this static class that provide the platform invoke calls to work with jobs. And so I need a few calls here. The first one is create job object. This is the initial call that creates the object and gives me the ability to get a handle back to it. And then I'm going to call the assign process to job object to kind of put processes inside the job. Now, once a process is inside the job, it can't really get out. Because if it could get out, it kind of makes the job a little bit maybe almost useless, because a process will just get itself out and be out of these limitations, but you can't. Once a process gets into a job, it's there forever and ever. And then the most important thing about jobs is the function set information job object, which is kind of a super function that has all the ability to set all those various limits that I mentioned. And so it has this job information class enumeration that has all these many options that you can find in the documentation, and I actually wrapped only a few of those. And so what I need to do here is create a job object, and then I'm going to call add process, and add process calls the assign process to job object. I'm accepting a process object here, which is one way to go about it, because there is a process class in .NET, so we can just utilize that. And then I'm going to just grab the handle from the process object and use assign process job object to add that process to the job. And then finally, when I want to set the CPU limit, I need to actually call the set information job object, which is again that monstrous function with the correct parameters. So the only way to do that is just to go to the documentation and see what the function expects to receive in the case of CPU rate limit. And so what we have here is a structure called job CPU rate limit information, which I've created here, and actually duplicated the structure that is in the Windows SDK, little bit simplified. The only thing you just need to remember from the interop perspective is use the struct layout with a sequential option. That's very important because in .NET the CLR is free to rearrange fields as it sees fit to fit things to be more efficient in some sense. However, in the C world or C++ world, the order of fields is mandatory, and it actually makes the compiler put them in memory in exactly the same order. So sequential tells the CLR, please don't rearrange my fields. The way I put them, that's exactly how I want them to be. So everything should work out just fine. And so now, if we look at CPU limit, this is what happens here. I'm getting a list of process IDs and the percentage, and all I need to do now is create a job. Here it is. I'm creating a job without a name, and then I'm parsing the process IDs, getting a process object from these IDs, and calling add process. And finally, I'm just setting the CPU limit using this %. I'm again parsing from the command line. So it can actually work on any process or a set of processes and just limit the CPU in this way. And so very simple to use, and once I have this job object, it's now reusable. I can use it in any process or any project that I want, and it's just there. And of course, I can extend it with time to have more functionality exposed through the class and then do the appropriate interop to make it work for me. So that's one example of using something that .NET doesn't provide out of the box. Now, jobs have been around for a long time, and maybe you even didn't hear about them at all. And that's fine, because up until Windows 8, in fact, they were almost useless. They were almost useless because there was that limitation where a process can only be part of a single job. So if a process was already part of a job, you wanted to put it in another job, you couldn't. And so since you couldn't predict upfront whether the process you're interested in is going to be in a job or not, maybe someone else put it in a job, then it wasn't that useful to work with. And so with Windows 8, this issue was solved with the idea of nested jobs. So now a process can be a part of several jobs, creating some kind of job hierarchy if possible. And so in this case, I can add a process to a job without any problem in most cases. In fact, that was created at least for UWP processes, at the time modern processes, because these are always managed as part of a job. In fact, if you go today to Process Explorer or other tools that show you which processes are under a job, you'll find that almost all processes today are part of a job, except for the system processes. Every process is actually part of a job. Even all the SVC hosts that are hosting services, the standard services in Windows, they're all part of a job because it's easy to do. And it's easy to manage these processes through the limitations and options provided by jobs. In fact, jobs have actually been extended in Windows 10, the RS1 version, the anniversary update. They support something called silos, which is the way Docker is implemented on Windows Server. And so silos are actually super jobs. They're actually jobs with some extended capabilities. Again, something you can research for yourself later on. And so here's a quick example of how nesting of jobs work. So let's say I have job 1, and I'm adding process 1 to the job, so it just adds P1 to job 1. And then let's say I want to add P1 to job 2, so essentially job 2 becomes a child of job 1. And child process can only provide extra limitations, but not the other way around. So they can be more limiting, but not the other way around. So if job 1 sets a maximum memory of 100 megabytes, then job 2 can specify 80 megabytes, but not 200 megabytes. That would simply fail. And so if I add P2 to job 1, that's fine too. If I add P2 to job 3, again, a hierarchy has been created. Job 3 is now a child of job 1. And I can add P3 to job 2, so P3 is automatically affected by these two jobs because this is the way it is right now. Maybe P3 didn't expect that, but that's life in this case. And if I add P4 to job 1, that's a normal thing. So today, jobs are much more useful than they used to be, something to think about when you want to limit resources or get some information about how resources are consumed with your processors, maybe part of some system. So here's kind of a quick round on the job API. It's really very small set of APIs. This is almost all of them. And again, the thing is that the set information job object is a super function. So everything interesting is actually right in there. So next, let's take a look at something related to thread priorities. So you may be familiar with the term of priority, and threads priorities in Windows are a number between 0 and 31, where 31 is the highest. And priority 0 essentially can't really be used. It's a special priority for a thread called the zero-page thread part of the memory manager, which we're not going to look at. So how do I set up priorities? Can I just say, hey, here's my thread, I really like it. I want to have priority of 20. That sounds like good to me today. Unfortunately, it can't really be done because the Windows subsystem, or the Windows API, if you will, imposes some limitations on how you can specify priorities. Just can't specify them as an absolute number, that's it. In fact, the way it works is you have a base priority for a process, sometimes called priority class, which is, in fact, the more official name. And then you can have several priorities around that base priority. So for normal priority class, what you get is that the base priority is 8, which means that all threads within that process have a default priority of 8. If you don't say anything, that's going to be 8. And that's typically the default because the normal priority class is the default priority class for most processes. You can just quickly take a look at Task Manager, for instance, and there's that base priority column. That's the priority class. You can see most of the things are normal. There are some other that are different, such as low and below normal. There's above normal and sometimes high, and maybe sometimes real time, which we'll get into. And so we have these 5 priorities in the middle, which .NET exposes. However, .NET, using the priority property of the thread class, doesn't expose the 2 special values called saturation values, which gives the priority of 15 and 1. So they're just not exposed by .NET for whatever reason. So let's say I do want to use them. Can I do that? And of course, the answer is yes. We need to do some creative coding, but we can do that. If you go to the above normal priority class, the same basic idea, just the default priority is now 10 rather than 8. If you go to the high priority class, again, the same idea. The base priority is 13. So you can increase priority by +1, +2, -1, -2. In .NET, that's it. But in the Windows API, it does provide a way to give us the 15 and 1, the 2 saturation values. The below normal, again, same idea. The base number is 6. The idle priority class, which Task Manager mistakenly calls low, but that's the same thing, has the base priority of 4. And finally, there's a real time, which actually has really high priorities, and you can actually get all the priorities from 16 to 31. So if you are getting excited about the real-time thing, don't get too excited. So Windows is not a real-time operating system in terms of the way operating systems which are real-time defined. And so real-time really just means higher than the rest of them. And real-time priority class has such high priorities which competes with many threads within the kernel. And so if you want to run with these priority class, you have to be running elevated with admin privileges. Otherwise, if you try to be real-time, what you'll get is high. So you will not fail, but you get high and not real-time, because in real-time, you're actually fighting for CPU for some very important kernel threads, and so that could actually damage your operating system in the way it works, and so this only is allowed for admins. And so we see these kind of segregation between normal priorities and real-time priorities. So one of the things that happens in normal priorities is that these priorities are dynamic. They can change by the kernel, by device driver. There's some mechanisms that are used to make the system more fair in some way. The real-time priorities, however, never change. So if you set a priority to some specific number, nobody's going to touch that. This is one of the differences between these two ranges of priorities. And so this is just the way it is. So how do we do these things? How do we change these things? So from an API perspective, for processes, there's the set priority class from the Windows API, and this in fact is exposed completely using the process class in .NET. So you can say a process, get current process, and then just set up whatever priority class you want. One of these 6 values that I've shown earlier. For thread priorities, so the Windows API is set thread priority. .NET, we have the priority property in the thread class, but as I mentioned, it has a enumeration which only exposes the middle 5 values. So if you want the 2 saturation values, you can't have it just like that. You have to do some work, which will show you what you can do to get one of these levels. So let's see a quick demo of that. So here's one Mandelbrot set. Let's create another one. I mean, just one is kind of boring. Let's have another one. So let's put them side by side. Let them fight for the CPU or something. And so one of the options I set here is that I can actually change the one of the processes to high priority class. So I'm clicking a button here. This is a toggle button, and it actually raises the process priority class to high. So if we can go to Task Manager, we can see that in fact this should be the case. So here are the 2 processes. We can see one of them is high and the other is in normal priority class. You can also do that with Task Manager, of course, but I've done that programmatically because this is mostly what we'll do in real life. And now let's see who wins. So I'll even have the normal priority class get a head start. So let's see. Well, I guess it was too much of a head start. Okay, I guess the demo gods may be playing around with me. Let's try again. What? Right. So it's not the demo gods, it's just me. Okay, so let's just try it again. That's 1. That's 2. Okay. That could have been very embarrassing. Let's see. So let's take the right one to be high. So I'm going to start this one and then this one. And notice the high kind of catches up because what happens in the Mandelbrot set in this case, what we have is there's a thread pool there that is doing all the stuff concurrently, and so they're fighting for the processors. And because the priorities are different, one is working with a base priority of 8, the other base priority of 13, it has a much higher chance on average to get the processor sooner. And so it kind of wins out. Let me show you the actual code here. So first, let's briefly look at the code from the Mandelbrot set that I'm using here. So the main loop of the thing here is just something that goes over all the lines in the bitmap. And then I'm using a parallel 4 here to calculate the color of each pixel on a specific row by using parallel 4. So I'm kind of using all the available threads, all the available processors on the thread pool. And so this should happen concurrently. And because the CLR is a per process entity, it has no idea that there's another CLR right beside it that also wants to use all processors. And so they're kind of fighting over the limited number of processors I have on my system. And that's why we get this kind of conflict. And so I'm awaiting this so the UI could still be responsive. And once the line is done, I'm writing these pixels into the bitmap. It's not the most efficient way to do this, but efficiency here is not really something I'm striving for this demo. but it is the way this application works. And so when I want to change the priority class, all I need to do, in this case, is just go ahead and change the priority class depending on that toggle button to high or normal. So to do this, I don't really need anything. I don't need to interop anything. This is actually available in .NET and is always been available. I can just use it. If I wanted to change a specific priority thread, that's more challenging if I want to use one of the two saturation values. And so the challenge here is that I need to somehow call the native Windows API, set thread priority, but I can't really do that because I need to get a handle to the thread. So if you try to locate a handle to the thread in the thread class, you'll find it doesn't really exist. And if you try to go to the .NET reference source, you'll see a field there called something that don't use, and that points to something which eventually holds the internal thread object, and then the thread ID is somewhere tagged in there. And so you can't really use these things. And the way I did that to get the proper handle, actually to get the ID so I can get a handle, is by using CLRMD, which is a very nice library related to debugging, which Christoph will talk about later today, but I'm going to use it in a very minimal way. And so what I've done here, I have an extension method that sets the thread priority, and to do that, what I did is use CLRMD to attach to the process in a passive way, which means I'm not actually attaching to anything. I just want to get some information about the process, and then I'm getting the runtime, and I can ask the runtime, give me list of threads. And then each thread object has the managed thread ID, which is exposed, and the OS thread ID. And so I can kind of make the connection and then use that to call the set thread priority on whatever thread we want to change the priority. So if I want to get the two saturation values, I can. So I'm not going to demo that, but you get this idea. So next I want to discuss briefly affinity. So affinity means on which processors should the thread execute. And so Windows always supported something called soft affinity using a parameter called ideal processor, which means that the thread will try to execute on that particular processor if possible. But there's something else called hard affinity, which is always respected. So if I say this thread can only run on this and this processor, Windows will have to respect that. So that's not good enough in some cases. So I can specify affinity in terms of process. Let's say I have a .NET process which is using the thread pool, which is the normal case. I can't really get every thread from the pool and try to say on which processors you can run. I can't do that. I want to say something which is kind of on the entire process. And so I can say that for the entire process, let's use 10 out of 12 processors, for instance. And I want to reserve these 2 extra processors for a specific thread, for example. Now, I can't do that with hard affinity because a thread affinity cannot escape the parent process affinity. And so CPU sets, which is a new feature in Windows 10, allows us to do that. So we can say, here's the default for a process, whatever thread I'm not specifying anything specific for that, let's take that default, but then let's have some special processors, maybe one, maybe more, that are targeted to specific threads. And so in this case, what I can do is say, hey, let's assume I have a very important thread. Maybe the UI thread is important. I want it to have a dedicated processor. And I don't want any other thread touching that processor. This is what CPU sets allows you to do. And again, this is something which is not exposed by the Windows API. Sorry, not exposed by .NET, and will never probably be exposed. In fact, there's a system affinity as well, which is used in Windows 10, in RS2 and later, with something called game mode. So game mode tries to kind of steer away the processor from your game. So the system itself, all the kernel thread stuff like that, is not going to use some processors, so your game can use those processors exclusively. And so that's more powerful, and in fact, it's not exposed through the Windows API, but only exposed through the native API. So you have these 2 APIs we can use, and then if you want to mess around with the system CPU set, you can do using this function. It's undocumented, but I actually wrote a tool for the book that does that, so it's kind of semi-documented. So here's a quick example of what that looks like. So I'm going to back to my two Mandelbrots, and I'm going to return them into a normal priority, both of them, and let them kind of run and see that they're all running fine. And it should be fine. And so one of them, I want to set a specific CPU set for thread 0, so the main thread. Okay, so the first thread, which is running the UI. So this is not a classic application to show these things, but still something that we can try. So I'm going to set CPU sets on the right one here, and we can try both of them. So the timing is not consistent because I'm projecting and because other stuff is running, so it's not a definite thing, but still, what you can do, you can, in many cases, get some benefits because you have dedicated processors for a specific thread or specific threads. And you can see I got a little performance boost because I'm using CPU sets. And so you can get these things for threads you care about. You want to make sure they have these processors available where the rest of the threads are using the default CPU set, which includes the thread pool. And because most of the application here is using the thread pool, they are staying clear of two processors that I have assigned for the main thread. So it always has a better chance of executing when it needs to, because it's doing a lot of work from the graphics and perspective and UI perspective. So again, to do that, this is not much more difficult than just doing normal interop. I'm going to skip that. You can get the code later and see exactly how it's done, because I want to cover some another feature. Okay, so in general, we have these objects called dispatcher objects, which are wrapped by .NET in terms of in cases where we need to do some synchronization. These dispatcher objects have the base class wait handle that allows us to call wait one, wait all, wait any, and stuff like that. You may be familiar with these classes, but there are other dispatcher objects that Windows provides. Let's say I want to use them. Can I extend this class hierarchy? And the answer is yes. I can derive my own class from wait handle, which is also a waitable object that I want to wrap, that .NET doesn't provide a proper wrapper for, and then I can just use the same wait functions with other objects. And so this is pretty easy to do. You just need to know exactly how to do it. So here's an example for a process. So you may think, hey, I have the process class. It exists in .NET. Why do I need a new wrapper? So the process class in .NET is really kind of an anomaly. It has no relation to wait handle. It doesn't inherit from wait handle. It inherits from component and stuff like that. It has nothing specific with that. But from the Windows perspective, a process is a dispatcher object. And so we can use the same mechanism to wait for a process or a bunch of processes or a bunch of processes and an event, whatever we want, to combine these objects in any way we want using the same API. So here's how to do it. I'm creating a process wait handle deriving from wait handle. In the constructor, I'm getting a process object and also go with a pure handle, and just I'm duplicating that handle for myself. Why? Because the process I get is going to be disposed at some point in time, and that handle will just go away. So I want to make sure to not go away. I'm duplicating another handle for myself that I'm going to manage. And I'm going to create a safe wait handle object with that duplicated handle and indicate that I want that safe wait handle to be the owner of the handle, and that's really it. All I can do now, for example, so here's a simple example I wrote for that particular purpose. Here it is. I'm creating several processes here, like some paints and notepads, and I'm waiting for all of them to complete. You can't do that with the process class. You can't. So in an easy way. So if I close every bit of these processes, maybe I should have created less processes. And once I close the last one, and I'm getting this notification that they're actually exited because I just called the wait one function, wait one method on my process wait handle. All right, so this is kind of the idea. So I want to kind of summarize because we're a bit out of time. There are stuff I wanted to cover, but not enough time, I guess. So we can actually look at the demo code. So the .NET framework is very rich. However, it doesn't cover everything. So you can experiment with things, look at the Windows APIs, look at things you can do using the platform. You can sometimes save you a lot of time and energy trying to accomplish things where other ways may be more costly and maybe even impossible. Thank you.